Hey everyone, in this video we're going to be talking about molar mass and how to find the molar mass of compounds using the periodic table. To start, we're going to remind ourselves of the definition of molar mass. So sometimes this is also called I'm going to write it up in the corner, gram formula mass, or just the formula mass. Just so you know, those are some other terms. But our definition of molar mass is the mass of exactly 1 mole of any substance in grams. So remember, 1 mole is 6.02 times 10 to the 23rd particles. We have different variations of particles depending on the type of compound or substance, atoms for elements, molecules for covalent compounds, and formula units for ionic compounds. But 1 mole is equivalent to that many pieces, so the molar mass is the mass in grams of that many particles. So what this allows us to do is this allows us to use the property of mass. I can measure the mass of a particular substance and use this relationship to determine how many particles there are. Generally, we stick with the unit of moles. It's not really practical to go to the unit of particles because those numbers are very large, bulky scientific notation numbers that aren't really practical to use. So ultimately, we just use the unit of moles. But what this allows me to do is to count by using mass, right? I can measure the mass of a substance, and that will then tell me the number of moles, or I can use that relationship to determine the number of moles. Okay? It's also important to know that the molar mass for each element can be found on the periodic table. Periodic table. So here is the square on the periodic table for gold. It is element 79. Okay, this right here is its molar mass. So 1 mole of gold is equal to 196.97 grams. Okay, so we're going to use those relationships to count particles by just taking a measure of mass. Okay, so we can also think about this conceptually and understand why different particles have different molar masses. If I were to think about a mouse versus an elephant, okay, a mouse is definitely smaller than an elephant. Okay, an elephant has more mass. What if I had a dozen? Okay, we're going to go ahead and indicate there. If I had a dozen mice compared to a dozen elephants, the dozen elephants still has more mass, right? It's just scaled up by a factor of 12 because it's a dozen. Okay, if I had a mole of mice and a mole of elephants, the mole of elephants still is going to have more mass because now I'm just scaled up by 6.02 times 10 to the 23rd times. Okay, the elephant is fundamentally a bigger animal, and so its mass is always going to be more. We're going to see that same thing with different compounds. The bigger the compound, or even atoms and elements, the bigger the element, the more stuff it has, the more mass it has, the more mass a mole is going to equal. Okay, so let's go ahead and do some examples. So to find the molar mass of a compound, we're going to use the masses of each element from the periodic table and just add everything up. Pretty simple. So we're going to do two different examples here. The first is water, H2O. So I'm going to use my periodic table. Okay. At this point, you should have your periodic table out to be looking at this, or pull up a periodic table online. I'm not going to pull one up here. I'm going to assume that you have one so that you can verify my numbers. Okay. Also, just as a quick side note, I generally like to keep 2 decimal places for all molar masses. Okay. 2 decimal places is my rule of thumb. So hydrogen on the periodic table has a mass of 1.01 if I round it 2 decimal places. And according to this formula, I have 2 hydrogens. Oxygen on the periodic table has a mass of 16.00. I only have 1 oxygen in this formula, and so I just add that up. 2.02 times 16, okay, is 18.02 grams. Now, units for this, okay? Some people will put grams per mole. Okay, that can be a little confusing. That is an accurate way to describe this, but I'm going to go ahead and write it in a little bit of a different format, one that we will be familiar with using for dimensional analysis. So 18.02 grams is equal to 1 mole of water. I really should put grams of H2O is equal to 1 mole of H2O. Let's look at the second example here. This is calcium phosphate. This one looks a little complicated, but if I break it down, this really means I have 3 calcium ions and 2 phosphate ions, right? That is the ratio here. Phosphate's just a big polyatomic ion. So I just need to count up all of the atoms of each element in this compound. So calcium has a mass on the periodic table of 40.08. Phosphorus, and I have 3 of them, right? 3 of them here. 1, 2, 3. Phosphorus has a mass of 30.97 grams, and I have 2 phosphorus atoms here. Oxygen has a mass of 16, and I have 4 plus 4, or 8 oxygen atoms. Okay, if I add all of that up, I'm going to get 310.18 grams of calcium phosphate is equal to 1 mole of calcium phosphate. Okay, so you can go ahead, if you want to separate these out, right, and do each of these little operations independently and then add them up, that's totally fine. However you feel like you need to do that. Anyway, you should get 310 grams of calcium phosphate for every 1 mole of calcium phosphate. The last thing I want to point out are compounds called hydrates. Hydrates are ionic compounds that have water molecules that have found their ways into the nooks and crannies of the crystal lattice structure of an ionic compound. So this is your crystal lattice here. Okay, notice there are some spaces in between those particles. And that is what allows the water to sneak in there. Okay, we can also remember that water is polar, so water has these slightly charged sides to it, right? A slight positive, a slight negative. And that is what allows the water molecules to stick to the ions, right? This slightly negative side of the water is going to stick to this positively charged magnesium. Okay, so that's kind of the explanation for why hydrates exist. But generally, the formulas look like this. We have the ionic compound formula, and then a dot, and a ratio of water molecules. So what this tells us that for every 1 unit of copper chloride, there are approximately 2 water molecules that have found their way in there. Okay, so this is a ratio. That's all. But that's all an ionic formula is anyway. So we're going to find the molar mass using the same way that we would anything else. We just add the mass of the water molecules to the total. Okay, so this is the compound copper 2 chloride, and we would call it dihydrate. Okay, dihydrate. We use those prefixes to indicate how many water molecules. So we're going to find the mass of this thing on the next slide. All right, so the same way we normally would, okay? We have copper. We have one copper atom in this formula. So we have fine copper on the periodic table. It's 63.55 grams. And then we have chlorine. Chlorine has a mass on the periodic table of 35.45. So each chlorine brings that. I have two of those. Okay, so that's 70.9. And then I have the water. So I'm going to go ahead and just do each atom like we're used to. Right, so water 1.01 times 2 for the hydrogen, and then I have 16, just one of those for the oxygen. Okay, but then I do need to think about the fact that I have two of these water molecules. So however you want to do that math, if you want to do the math with just multiplying for each atom, if you want to multiply for the whole molecule, however you want to do that, you just need to take that whole thing into account twice. So we're just going to add all of that up. So copper 63.55 plus the 70.9 from the two chlorine atoms. Then we have a total of 2 times 2, 4 hydrogens and 2 oxygens. That is going to give me a total mass of 170.49 grams of copper 2 chloride dihydrate in every 1 mole of copper 2 chloride dihydrate. Okay, this ultimately is your answer. All right, thanks for watching.